Greetings everyone, and welcome to a Kinematics and Dynamics of Machines lecture. This will be lecture 8, based on Wilson and Sadler, Kinematics and Dynamics of Machinery. Tonight we're going to be starting chapter 4, which is Acceleration Analysis of Mechanisms. As per our normal procedure, we'll talk about basic concepts, and then we'll start generalizing those out to look at specific linkages. Tonight we're going to be talking about the analytical vector methods that can be used for acceleration analyses of some basic mechanisms. The homework problems are 4.1 and 4.6, and as always I expect and strongly suggest that you read through, or at least go through, the relevant sections of the book, and that in particular you take some time to look at the sample problems that we reference during the lecture. Alright, so let's start with some basic concepts. In Chapter 2 on Wilson and Sadler, we went through position analysis, and we learned that we can treat mechanisms as a series of vectors that make a closed vector loop or vector chain. And if we have a 1 degree of freedom mechanism, that if we can determine one of the link positions, we can calculate all of the others. In Chapter 3, we did something similar with velocity, just noting that the velocity is the first derivative of the position. And again, with a 1 degree of freedom mechanism, if we know the velocity of one link, we can find the velocities of the others. In Chapter 4, we're going to be carrying those same concepts forward to look at acceleration. And of course, this is important because we all remember Newton's second law, which is that force is equal to the mass times the acceleration. So prior to this point, we haven't really cared at all about the mass of anything. We're only looking at the kinematics of the system, which is just the motion, not really caring too much about the forces. As we now go into acceleration analysis, we're laying the groundwork to look at the dynamics, hence the kinematics and dynamics of machines that characterize this course. We remember that velocity is a vector that's representing of change in position per unit time, and acceleration is a vector representing the change in velocity per unit time. And of course, if they are vectors, that means that they have both a direction and a magnitude. So, just to reiterate something that we looked at previously, we looked at position of a point and talked about how we would get the velocity of that point. In the same way, we can look at a point with a velocity and note that the acceleration, in this case angular acceleration, is equal to the derivative of the angular velocity with respect to time, and that we can break this up or set it into components where we are looking at that angular velocity with a direction of the I, J, and K axes, so the directions of our primary coordinate system. In a plane, remember, the vector direction of alpha is perpendicular to the plane of the rotation. At this point, it's appropriate for you to take a quick look at sample problem 4.1 on page 261. It's a fairly simple problem, so it shouldn't take you very long. If you want to pause now, it's a good time to take a look. Alright, I'm sure now that you've looked at sample problem 4.1. Now, what we're looking at in this class primarily is motion of rigid bodies at fixed points, and primarily we're looking at that in the context of linkages. So we learned in Chapter 3 that the velocity of a point in a rigid body that's rotating about a fixed point is equal to the cross product of the angular velocity with the vector that describes the position of the point. If we're trying to get acceleration, we know that taking the first derivative of this cross product gives us the acceleration. In this case, we know that the angular velocity can be changing with respect to time, so we would need to take its first derivative when we have a fixed position, but also that position of the point can change with respect to time. So we end up with these two cross products that are needed to describe the acceleration of our point. We can break that up, or at least restate it a little bit, in noting that this first cross product, omega dot cross r, is actually described as alpha cross r, alpha being the angular acceleration. And then omega cross r, by definition, if you look back at the Chapter 3 notes, can be described as the change in the direction of that vector, the acceleration vector. Each of these two cross products, omega cross r, omega cross r, and alpha cross r, are looked at as a specific component of the acceleration vector. The alpha cross r is tangential acceleration. Tangential meaning that it is at a tangent to the path of the point. If we look at this rigid body, r, which has a fixed point O and a moving point B, the tangential acceleration then is 90 degrees to that straight line between the moving point and the fixed point. The next component, omega cross r, is the normal acceleration. This is another one of those things that you're going to hear me say an awful lot in class. The normal acceleration has a direction that is from the moving point, in this point, in the case point B, towards the stationary point, in this case point O. Remember that the tangential and normal accelerations are both vectors. So in order to get their sum, we must calculate this hypotenuse between the two vectors. So this total acceleration would be the square of tangential acceleration plus the square of the normal acceleration, and then you'd have to take the square root to get the actual tangential acceleration. This is explained further and run through a problem, sample problem 4.2, which is on page 263. Again, I'd recommend that you pause the video at this point and at least read through that problem to acquaint yourself how this works. So now that you've gone through that sample problem, hint hint, we can also start taking a look at the potential of moving coordinate systems. We did this when we looked at velocities, and we came up with this equation to describe the motion, or the velocity of some point in a moving coordinate system, where that moving coordinate system can also be referenced back to a stationary coordinate system. So, if we're looking at the acceleration of that point, we would again differentiate our equation, and we'd end up with this rather long equation. Some of these will be very easy to determine, some of them may be less so. We've looked at omega dot cross r. This is the same thing as alpha cross r, so this is the tangential portion of the acceleration. Omega cross r, this is the normal portion of the acceleration. And then we have this other last term, 2 times omega cross r dot. This is the Coriolis acceleration. You may have heard of the Coriolis acceleration before. It's more often noted now in things like weather forecasting, as we look at the force or the acceleration, the force that causes a hurricane to spin. but it also has its place in mechanical engineering. I do like to give you the definition of the Coriolis acceleration because it's kind of intriguing. It's a fictitious force exerted on a body when it moves in a rotating frame of reference. The byproduct of measuring coordinates with respect to a rotating coordinate system. So that's when you see it, and that's why you see it in meteorology, because the Earth is a rotating coordinate system, and we are measuring coordinates with respect to it. So just kind of a neat crossover. In addition to the things that we've already looked at, there's an analog with the relative velocity that we looked at in Chapter 3, the relative acceleration. So again, we look at the relative acceleration A of c as equal to the acceleration of some fixed point b plus, I shouldn't say the acceleration of a fixed point, that was kind of silly, acceleration of a fixed point or a reference point for c, plus the acceleration of c with respect to b. And again, we can break this down into normal acceleration of c with respect to b and tangential acceleration of c with respect to b. And just to make things very, very explicit, when we're looking at the velocities and then using those to calculate the accelerations, we know that the angular velocity of c with respect to b can be seen as the velocity of c with respect to b divided by the length between the 2 points, and we can then use that definition for the normal and tangential. Alright, so those are the preliminaries. Now let's see how we actually use these things to analyze a 4-bar linkage by analytical vector methods. So here's our familiar 4-bar linkage. We have our fixed link, our crank, coupler, and rocker, and we know that if we add the vectors together, the vectors which make up this figure, they sum to 0. If we differentiate it and substitute for the velocity equation, we again sum to 0, throwing out our fixed link, which isn't moving, so it has no first derivative for velocity. We can then differentiate that equation and end up with this gigantic long one, which again has the components that hopefully are becoming a little familiar as I repeat them: alpha cross r and omega cross r. At this point, when I say that, you should immediately be thinking alpha cross r, tangential, omega cross r, normal. Now, the last two terms in that previous equation, very long equation, represent the negative of the total acceleration of point C in that 4-bar link. From that previous acceleration, then we can take the relative acceleration concept and simplify that equation a little bit. Then, if we look at alpha cross r, which is our tangential acceleration in the xy plane, it's very easy to take the product of this matrix in order to get a simplified equation for alpha cross r. Same for omega cross r, and as then carry it forward, we need to do omega cross r. We end up with some somewhat simplified equations. You may want to take a moment and just multiply these out in order to confirm for yourself these are correct. So, we take that gigantic long equation from a couple of slides ago and substitute in what we just did for the equations for alpha cross r and omega cross r, and we end up with this nice long equation. At this point, we have something that we can get hold of. Remembering that this is a 1 degree of freedom mechanism, if the position, angular velocity, and angular acceleration of one of the links, in this case usually the driver, is known, and the position and velocity for the other two links are solved for, as we learned how to do in chapters 2 and 3, then we can solve for all the angular accelerations of links 2 and 3. So simplifying a little bit, generating two simultaneous equations, we can rewrite this into matrix format and come up with the following. Noting that your book, which we are using the same nomenclature, does like to simplify some of these equations. So we have first a couple of intermediate calculations for what they call A and B. We can then use A and B and another intermediate calculation for D to come up with specific calculations for alpha 2 and alpha 3, the angular accelerations of the coupler and the rocker. Now, this is worked out in sample problem 4.3 on page 269. I will intend to run through this very quickly in class, but as always, I strongly suggest that you take a look at the sample problems that I note in the lecture notes, read through them in the book, so that you're ready to follow along in class. That will end our lecture for this evening. We will then be moving forward into the rest of chapter 4, in our next lecture. That will be covering a graphical technique to also calculate angular accelerations. It's quite similar to the angular velocity techniques that we've already looked at, but has some additional complications. So, please take a look again at this lecture, rerun any portions that you want to again, and do take a look at the relevant sections in the book. I'll look forward to seeing you in our next lecture. Have a good evening.